Okay, ladies and gentlemen, you are welcome. In this video, we are going to look at the concept of permittivity in electricity. Don't forget that in my previous video, we actually discussed about Coulomb's law, where we have a formula that relates force is equal to Q1 K Q1 Q2 all over R square, where K it appears as a constant and it has, of course, a constant value, and the constant value, which is k, is equal to 1 all over 4 pi permittivity of a free space. In this concept today, we're going to look at the concept of the permittivity of a free space or permittivity in general. So now, what is permittivity? Permittivity is a measure of a material's ability to resist the formation of an electric field within it. So we can have different material, and different materials have different permittivity. And this permittivity, it is actually the measure of how material can resist the formation of an electric field within it. What is electric field? Electric field is a region where an electrical pulse experience. So let's say you have two materials. Let's say you have material A here and you have material A here and you have material B here. And let me say you also have material C. So these materials can have the ability to produce or to generate or to form an electric field within it, or electric force within it. So permittivity is actually a measure of the material's ability to resist the formation of an electric field. It means that the higher the permittivity, it means the more resistance in terms of the formation of electric field. So the higher the permittivity, the lower chances the material can form an electric field within it. So therefore, permittivity is an indication to show or to indicate that whether a material can be used as can be used to conduct or can be used as a something that can be used in generating electricity, like a wire. So different materials, different wares, they have their own permittivity of a free space. So they have their own permittivity. So the lower the permittivity, the best the material can be used for generating an electricity. Because when you have high permittivity, it tells you that materials or that objects cannot form an electric field within it. And it determines how much electricity is reduced inside a material when it is placed in an electric field. So this is also very interesting that you should understand that this permittivity can determine how much electric field is reduced inside a material when it placed in an electric field. And the symbol for this permittivity is epsilon. As we can see it from here, it's represented as epsilon, and it plays a crucial role in understanding electrical interactions in material. So as we can see also from this angle, that electric permittivity is a measure of how much electric field is reduced in a medium compared to a vacuum. And we have a formula for calculating permittivity. This permittivity, it means absolute permittivity. And then we have the epsilon naught, it means permittivity of a free space, as we can see. So this is actually formula that shows the relationship between the permittivity of a free space and also relative permittivity. So this is, of course, the absolute permittivity, and the epsilon r here, it means the relative permittivity, or we can call it dielectric constant of a material. So this is actually a formula that shows a relationship between absolute permittivity of a free space, and then relative permittivity. So now, permittivity influences the capacitance of a capacitor, affecting how much charge can store. So one very interesting things, ladies and gentlemen, with this permittivity, uh, it can influence the capacitance of the capacitor, affecting how much charge can store within it. So the higher permittivity of a materials allow more electric flux to pass through them for a given electric field. So this is to tell you, ladies and gentlemen, uh, if you have the permittivity, it can actually tells you how good materials can be in terms of storing an electrical charge. So that is why it affects the capacitor. And the formativity of a free space, which is epsilon naught, is a constant value, which is approximately 8.854 times 10 raised to the power of minus 12 farad per meter. Farad per meter is the unit for the capacitor. So this is actually some of the examples of different materials with their dielectric constant and their formativity. So you can see the vacuum has a dielectric constant of 1.00, that is the formativity. Air has 1.00059. So you see that the formativity of a material varies. So it varies from one material to another. It's not the same. So you should get that. And then the next thing is the types of formativity. So the types of formativity, we have two. We have absolute formativity. We have absolute formativity as number one, which is represented as epsilon. And this absolute formativity, it refers to the formativity of a specific material, including its dielectric properties. So that is the absolute formativity. So it's actually trying to define the specific materials with their dielectric properties. And then we also have relative formativity. So the relative formativity, also known as the dielectric constant, compares with a material's formativity to that of a free space. So that is why relative formativity, it is relative. You use it as absolute formativity because the formula of relative formativity, as you can see, it is the same thing as the absolute formativity divided by formativity of a free space. So this is actually a formula for calculating relative formativity. So the dielectric constant varies across or among materials and influences their suitability for use in electric and electronic applications. So this dielectric constant, that is the formativity of a material, it varies from one material to another, and that also influences their suitability for use in electrical and electronic applications. You know that we have different materials, we have different wear, we have different materials that can be used in electrical and electronic applications. So that applications depend on the dielectric properties or the electric constant as well as the formativity that particular material. So then what are the applications of and significance of this formativity? So formativity is a fundamental in designing capacitors, insulators, and other electronic components. So when you are going to design a capacitor and other electronic materials, so you have to look at the formativity of the materials that you are going to use. Very important, because as you can see, there's a strong relationship between the capacity of a material and of course the formativity or the absolute formativity of that material. So you can see uh, C here stand for capacitance in farads. And then we have epsilon, which is actually formativity of dielectric or absolute formativity. And we have area, and then we have the distance. So therefore, we should understand that this formativity is very, very important. And of course, this formula, we are going to use them in solving so many problems, including the first formula of the absolute formativity is equal to relative formativity times formativity of every space. We are also going to use this formula to solve some problems. So understanding formativity, formativity, it affects the electromagnetic wave propagation and also the behavior of antennas and transmission lines. Therefore, understanding formativity helps in developing better insulating materials and optimizing electrical systems. So this is the applications of formativity of a free space. And ladies and gentlemen, don't forget to actually try to understand how this electric formativity or formativity of materials are, because it is very important and it's something that you usually ask in the exam. So thank you very much and see you next in my next video.